Since we started talking about length, areas, and volumes, we've considered different things. We started with measurements, we continued to line segments and all that, and then we started taking the shapes one after the other, starting with triangles. And from that point onwards, that's about polygons actually, because a triangle is the polygon, is the smallest, is the polygon with the smallest number of sides you can ever have. Okay. So here proper, then afterwards, of course, we talked about quadrilaterals, squares, rectangles, rhombuses, kites, parallelograms, and of course, trapeziums. So here we are talking about regular polygons and tessellations. I mean, the idea of tessellation may be looking new, but basically, if you have seen tiles before, or if you have seen, you know, people covering a wall with maybe wallpapers and things like that. So you already have an idea about what tessellations is about. So let's go ahead and see regular polygons and tessellations. Let me even be sure what the pronunciation of that should be. Tessellation, meaning, okay, tessellation. Okay, yeah, been doing a great job. Tessellation. Okay, yeah. Regular polygons and tessellations. First of all, let's talk about regular polygons, focusing on the idea of side, perimeter, and of course their angles. So first of all, let's talk about the key definitions as far as polygons are concerned. First, we know, I mean, before now, we've been saying that a polygon is actually a flat shape made of straight line segments that meet at end points. Okay? It's a flat shape made of straight line segments that meet at end points. So, in essence, a polygon will be something like this. You have a line, you have another one, and so where one stops, another one starts, and then at the end of the day, they all join up. That's a polygon, right? But the only thing is that we know that this is a triangle. Another polygon would be draw this line, draw this, where it stops, draw another one, and then until everything closes up. That is a polygon. And another one is you have this, you have this, you have this, you have this, and you have this. That's a polygon, right? So that's what a polygon is basically about. So a flat shape made of straight line segments that meet at end points. So then when we talk about a regular polygon, we are saying that in that case now, all sides are equal in length and all angles are equal in measure. Okay? So examples of regular polygons include, I mean, I've talked about this a lot. Equilateral triangle, three equal sides and three equal angles. So in this case now, you have the smallest regular polygon is an equilateral triangle. So you have all the three sides equal and all the three angles are also equal. Since we already know that for any triangle, the side facing the triangle is proportional to the angle that is facing it. So in essence, we are saying that if you have a triangle, right? Let's say you have a triangle and this is 30 degrees, this is 70 degrees, that's 100, right? And then this is 80 degrees. So automatically, the side facing 80 degrees will be the biggest, the side facing 70 will be the second biggest, and then the side facing 30 is the smallest. So we have that proportionality thing going on for triangles. But if for an equilateral triangle, all the sides are equal, all the angles are equal. And because the angles in a triangle in any triangle add up to 180 degrees. So here now we have that angle A plus angle B plus angle C, okay, plus angle C is equal to 180 degrees. And here for an equilateral triangle, we know that angle A is equal to angle B is equal to angle C, and that will just be 180 degrees divided by 3. So it means that each of these angles is actually 60 degrees, like that. Okay? So all the sides are the same and all the angles are the same. So we have that. Then the next regular polygon would be a square with four equal sides and four right angles. Four equal sides and four equal angles, technically. And it happens that okay, for a square now, I can use the grid. This is 1, 2, 3, 4. 1, 2, 3, 4. This and this. Okay, this is equal to this, equal to this, equal to this. So we already know. So if we have this to be A, B, C, D, so we know that angle A plus angle B plus angle C plus angle D is equal to 360 degrees. And that's 4 now, right? So for a square like this now, mm, so all the angles have to be equal. So angle A now is equal to angle B, is equal to angle C, is equal to angle D, and that will be 360 degrees divided by 4. So that's 90 degrees. That's why all the angles are right angles like that. So 90 times 4 is 360 degrees. So that's so equilateral triangle, regular polygon, square, regular polygon. And then going from pentagon upwards to now begin to talk about regular pentagon, regular hexagon, regular octagon. So for instance, a regular pentagon is a five-sided polygon that has all the sides equal and all the angles equal. So you have this. I hope I can try here. So this. It may not be perfect, but I mean, just as with the stroke, just assume it's equilateral. It's all the sides are equal. It's not looking technically it's not equal like that, but based on the strokes I've drawn. So let that be your guide. So in this case now, we know that angle A plus angle B plus angle C plus angle D plus angle E should be equal to 360 degrees, right? So, and since we're talking about an equilateral, a regular pentagon now, so it means you have, okay, here we have regular pentagon, five sides, five angles. So this side, all the angles are the same. They're equal. And since all the angles are the same, so it means that angle A plus angle B plus angle C plus angle D plus angle E is equal to 360 degrees divided by 5, which is 72 degrees. So it means each angle will be 72 degrees each. So each of these angles is 72 degrees. So here we've seen square already. That's a regular, uh, quadrilateral, regular polygon. And this is equal-sided triangle, equilateral triangle right here. Okay. Then we have equilateral triangle, square, regular polygon, pentagon, and so on and so forth. Okay. So with that out of the way, let's move on to talk about other things for a polygon. So examples of regular polygons. Okay, we've talked about that. So for instance, let n be number of sides and s be the side length, right? So we have number of sides and the length of the side, for instance. So, and that leads us to the idea of perimeter. So we can then talk about the perimeter of a regular polygon. Because all sides are equal, then we simply say perimeter is the number of sides times the side length, where P is the perimeter of the polygon. So we can now take this idea back to what we've been talking about before now, that so if you now want to talk about perimeter, so perimeter here, of course, you know this will be side A, side B, and side C. So perimeter here is simply okay. Well, since all the sides are the same, right? Okay, I mean beyond that now, we know all the sides are the same. So this is SSS in short. So perimeter will simply be number of sides for a triangle that's 3, then the value of the side as S, so that'll be 3S. So if S is say 8 meters, so that means we just have 3 times 8 meters. Okay, and that will be 24 meters like that for that equilateral triangle. For square now, of course, S one all the sides are S each, so S S S S. So the perimeter is simply number of sides, that's N times S. So that's 4S here. So imagine if S is 8 here, you have 4 times 8 meters. Its perimeter is still a length, so you have 32 meters in that case. Okay, you have the same thing for a regular polygon. You have S, 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 S. So, of course, I don't have to write all that. Once I write one and you can see the stroke telling you that they are all the same, so you can already agree that perimeter is number of sides times the side length. So that's NS, and that is 5S in this case. And if S again is 8 meter, like before, so you have 5 times 8 meter, and the perimeter is 40 meter in that situation. So, right? So that takes care of the idea of the perimeter of a regular polygon. So because all sides are equal, perimeter is P perimeter P is number of sides times the side length, where P is the perimeter of the polygon. So in example one now, we have perimeter. You want to get the perimeter from the side length, okay? So a regular pentagon, that means n is equal to 5, has side length 7 cm. Find its perimeter. So n is 5, s is 7 cm. So perimeter is n times s, that's 5 times 7, which is 35 cm. Answer, the perimeter is 35 cm. So I've done something like that over there already. So that's why I'm not wasting time with this. So interior angles of a regular polygon. Now, for any n-sided polygon, the sum of interior angles is n minus 2 times 180 degrees. So for a regular polygon, where all angles are equal now, you can say that each interior angle is actually okay, I think I made a mistake with what I did here. Okay, for this now, 3 times n minus 2, 5, that's 3 times 180. This should actually be 540. Yeah, that was a mistake I made it. That's 540 degrees. And this is okay. Yeah. Um, this is 540 degrees. This is 540 degrees. So that is multiply by 2. That is 1080. This is like 108 degrees for one angle. I think so. Yes, 108 degrees. Sorry, that was my bad. Okay. So now this angle thing is going to take care of all of that now, right? So interior angles of a regular polygon, for any n-sided polygon, sum of interior angles is n minus 2 times 180 degrees. You'll be wondering why this, but I'll show you very soon. For a regular polygon, all angles equal. Each interior angle will be interior angle, that's n minus 2 times 180 degrees equals all over n. So use the formula with ordinary fraction if you are writing by hand, right? So n minus 2 times 180 degrees over n. So, okay, that's interior angle. Let's quickly settle that. Why is the sum of interior angles n minus 2 times 180 degrees? Let's go and check one after the other. Now, we know one basic thing. We know, let's say, sum of interior angles now. Or better still, let me just say interior angles. Interior angles. Okay? So from what we learned so far, we know that for a triangle, uh for any triangle, the sum of all the angles will be 180 degrees. So if this is A, B, C, right? So all these sides are equal, all the angles are equal. We know already that the angle A plus angle B plus angle C is equal to 180 degrees. And since each one is equal, so we say, so this is the sum now, sum of interior angles. That's the angles inside, interior angles. Okay. Then angle A plus angle A now is equal to, I mean, I've done this before, but I'm doing it again. Angle B is equal to angle C. And since three of them are equal, so we just divide, each angle will be 180 over 3. That is 60 degrees. So this is uh an interior angle, that's one of the interior angles. This is an interior angle of that triangle. Now let's come to this now. This is for this is for equilateral triangle. Now equilateral triangle. Okay, equilateral triangle. So you see, so this is more like the basis of the whole thing. This 180 degrees, pay attention to it. Now, check this out. You have a square now. You know, if you have a square is a regular pentagon. It's a regular quadrilateral. So for a square, imagine you have this 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And you bring this down. Okay. So this is A, B, C, and D. So if you have this diagonal, so you see, this has been divided into two triangles, right? It has been divided into two triangles. And you know, the sum of an interior angle of a triangle is 180 degrees. So this is 180 plus 180. So that's why the whole thing is going to be 360. So you see now that here, sum of interior angles, sum of interior angles is equal to 2 times 180 degrees, because we have 180 here, 180 here. okay? Because these are two triangles, and that gives us 300 and of course, you know, the number of sides here is equal to 4, okay? So the number of sides is equal to 4. So you see now this is actually, so this 2 here is the same thing as n minus 2 times 180 degrees, right? So, okay, of course, we already know that this is 360 degrees normally, but this formula actually holds true here. So we take that idea again to say a regular pentagon, and we see the same kind of trend. So you have, for a regular pentagon, you have this, this, and this. Okay, all the sides are the same. It may not be looking like that really. So all the sides are the same. But guess what? So if I draw a line from this corner here, and I draw a line from that same corner here, so I have three triangles in this case. And each triangle, the sum of its angles is 180 degrees, right? So if this is A, B, C, D, E. So we're saying that there are three triangles here, so that we can now say that sum of interior angles is equal to, sum of interior angles is equal to 3 times 180 degrees. And don't forget the number of sides here is 5. And you know that is 540 degrees, of course. But then this is the same thing as 5 minus 2 times 180 degrees. Okay? That also validates the fact that n minus 2 times 180 degrees is the sum of interior angles. Okay? So of course, if you want to find one of the angles, you just divide 540 by 5. If you want to find one of these angles, you just have 360 degrees by 4, which is 90 degrees. So we can say here an interior angle, an an interior angle, an interior angle will be 360 degrees divided by 4. That is 90 degrees. That's the right angle. So here, an interior angle will simply be 540 degrees divided by 5, which is 108 degrees. So it means each of the angles is 180 degrees. I know I made a mistake here before. Should be 180 degrees. So this is 180 degrees. So for this same one now, so each angle here is 180 degrees. So generally speaking, you can continue the same thing. So generally, okay, sum of interior angles, sum of interior angles. So for a a regular polygon, generally for a regular polygon, sum of interior angles is n minus 2 times 180 degrees, like that. Okay. Then an interior angle, that is one of the angles. Now, since they are equal, will just be n minus 2 times 180 degrees divided by n. Okay? So, like all the things we've seen before now. So, okay, that's about interior angle. So before we go too far, we also want to talk, okay, well, okay, let me take an example that is not even here, that is not on the on that page. So maybe I can say find the sum of interior angles, find the sum of interior angles of a regular decagon, of a regular decagon. Also find the value of one interior angle. Okay, one interior angle. So here, the most important information right here is this regular decagon. This regular decagon, that's the most important information we ever need from that it is a regular decagon. Okay. So first of all, the solution, of course, a decagon has 10 sides and 10 angles. Okay, first, that's the deal. So that means that n is equal to 10. Okay, so we can then say that sum of interior angles, sum of interior angles is equal to n minus 2 times 180 degrees. That's 10 minus 2 times 180 degrees. That is 8 times 180 degrees. 8 times 0 is 0. 8 times 8 is 64, hold 6. 8 times 1 is 6. I mean, 8 times 1 is 8 plus 6, that's 140. So the sum of interior angles is 1440 degrees. Then on the other hand now, an interior angle, an interior angle is equal to, of course, n minus 2 times 180 degrees all over n. Of course, we've done that already. We know this is 1440 degrees divided by 10. Okay. So we then have 1440 divided by 10, that's 144 degrees. So one interior angle of a decagon is 144 degrees, like that. Okay. So, yeah, so now we move on to the idea of exterior angles. So the sum of all exterior angles of any any convex polygon rather, is 360 degrees. So any polygon at all, whether it is regular or not. But for a regular polygon, all exterior angles will be equal to the uh, uh for a regular polygon, all exterior angles we are equal, right? So it means one exterior angle will be 360 degrees all over n. So at each vertex, interior angle plus exterior angle is 180 degrees. So this is really important for us to understand. So now look at this. Now want to talk about exterior angles, as you have seen. So we're talking about exterior angles. I think it's about time I need to change some of these markers. Can I overhaul the whole thing? I'm bringing in this light blue thing. What else do I need to change? Let me change this to say this deep green. So let's go. So now we're talking about exterior angles of exterior angles of polygons, exterior angles of polygons, whether regular or not. So the the sum of exterior, the sum of exterior angles of a polygon, like we said already, is 360 degrees. I'm going to show that to you very soon. Okay. So for a regular polygon, for a regular polygon, an exterior angle, okay, is equal to 360 degrees divided by the number of sides, because they are all equal in that case because of that regular thing right there. So can we show this? First of all, let's start with an equilateral. Okay, in fact, let me start with any kind of polygon. Let me just start with any kind of triangle before I even go for regular triangle, which is equilateral. So imagine this triangle now, and then this angle is 70 degrees. This one is 50 degrees, and then of course that's 120. So this makes it up to 180 degrees. Now, see what happens here. So if you imagine you now extend each of this now. If you extend these angles, what happens? So now you have this angle here. I know angles on a straight line add up to 180 degrees. So this is going to be 180 degrees minus 60 degrees, and that is 120 degrees. So keep this. Then coming here, you have this angle. That is simply because there are two of them are on the same 50 plus whatever is here is 180 degrees. So 180 degrees minus 50 degrees is equal to 130 degrees. So you keep that also. Then coming here, this angle plus 70 is 180. So it means that this angle is 180 degrees minus 70 degrees, which is equal to 110 degrees. So sum of the exterior angles now will just be, so we have, let's start from 110 degrees plus 120 degrees, this one, plus 130 degrees. So add everything. You have 0 there, you have 6 here, you have 3. So you see, the sum of exterior angle is 360 degrees, like that. And this is for a regular, this is for an irregular, is an isosceles, no, this is a scaling triangle, right? So, because if you look at this now, this is this side is not equal to this side, is not equal to this side. So that's a scaling triangle. So what if we now use an equilateral triangle? Imagine an equilateral triangle where you have something like this. So all the sides are equal. So automatically all the angles are equal to. So let's imagine, of course, we know the each angle with 60 degrees automatically. So imagine you have this, you now have this. Then you have this. I mean, you can go anyhow you like for sure. So, this is 60 degrees and this is 60 degrees. So automatically, this angle is 180 degrees minus 60 degrees. That is 120 degrees. So, of course, this one too is 180 degrees minus 60 degrees. That is 120 degrees. Here too, you have 180 degrees minus 60 degrees. That is 120 degrees. So sum of the exterior angles now. The exterior angles is simply equal to 120 degrees plus 120 degrees plus 120 degrees. And that is 360 degrees easily. So you see it is true always. So in that case now, an interior angle, we already know this one is 60 degrees already, right? So, but before we establish that formula, okay, I've already established it that the sum of all the exterior angle is 360, but then one exterior angle is 360 over n. So I'm going to do something in that line. So let me go on to the next one and say, okay, I've been doing triangle, rectangle, and pentagon. So let me go for a square now. Let's do a square. Imagine we have this square. That's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, right? So imagine we have this square. All the sides are the same. Okay. We know each angle is 90 degrees. So imagine we now extend each one anyhow we like. We extend this one this way, extend this one this way, extend this one this way. Anyhow you extend it. You could as well extend it this way, whatever. So now imagine this now. So if you now go ahead and subtract, angles on a straight line is 180. So if there's 90 here, there's also 90 here. So it's just 90 degrees. So here too, 90 degrees because 180, or maybe I should just show that because this is 90 degrees already. So this green one now is 180 degrees minus 90 degrees. That is 90 degrees. So here too, 180 degrees minus 90 degrees. This is 90 degrees. So here you have 180 degrees minus 90 degrees. This is equal to 90 degrees. And coming here, you have this too. 180 degrees minus 90 degrees. So this 90 degrees subtract. So you have another 90 degrees. So again, we say sum of exterior angles, sum of exterior angles will simply be 90 degrees plus 90 degrees plus 90 degrees plus 90 degrees. That is 360 degrees easily. Okay. So we move on to the next one, where we talk about, say, a regular pentagon. Regular pentagon. So for a regular pentagon, it is five-sided, all sides equal. Okay. So we have this, this, this. Okay, this and this. So regular pentagon, right? So we know that for a regular pentagon, I think we found that each interior angle of a regular pentagon will be, okay. I mean, I think we got that before. So let me just go and pick it up so I don't keep stalling on that. Of a regular pentagon, for a regular pentagon, each interior angle is 180 degrees. Okay, we know that that's 180 degrees. So this is 108 degrees. I think I need to change this up. Okay, let me come for this. So each interior angle is 180 degrees. So that means that we have 108 degrees, 108 degrees, 108 degrees, 108 degrees, and 108 degrees, right? So if you like, anyhow you want to extend it, you can do that. So you can do this extension, you can extend this way, you can extend this way, you can extend this way. If you also choose, you can extend this way, whatever. So, but whatever it is, as far as it is a straight line, then this one you can extend this way so that by the time you come back here, you can then have this is now 180 degrees minus 108 degrees. That is 72 degrees. So one exterior angle is 72 degrees. So what happens? So of course we know that everything is going to be 72 degrees like that. So 72 degrees, 72 degrees, and 72 degrees. So sum of exterior angles, sum of exterior angles will simply be 5 times 72 degrees, which is simply 180 degrees, right? So we have that. Yeah, so 5 times 72 degrees is 180. For a moment, this is looking like, so if you take 2 out of this is 10 times 36. Oh, sorry. I just knew something was not right. So 5 times 72 is like 5 times 2 times, I mean, 72 is 36 times 2. So 5 times 2 times 36, that's 360 degrees. I was wondering when I wrote 180 degrees, it was looking strange. Okay. So that's what we have. 5 times 72 degrees is 360 degrees. So now you can see we have established beyond all doubts that sum of exterior angles, sum of exterior angles of any polygon, you don't have to calculate, it's 360 degrees. Okay. Then an exterior angle of a regular polygon, is simply 360 degrees all over n, because for a regular polygon, all the sides, all the angles and all the sides are the same, right? So I'll just take a simple one before we go. So find, or better still, what is the value? What is the value of one exterior angle of one exterior angle of a regular polygon with 12 sides. Okay, well, let me say with 20 sides now. With 20 sides, polygons can have as many sides as possible with 20 sides. Okay, so what's the simple answer here? The simple answer will just be this, that first of all, sum of exterior angles, if you like, you can call it SE. Sum of exterior angles of a polygon, of any polygon at all, is 360 degrees. And for a regular polygon, theta exterior for an exterior angle will be sum of exterior angle divided by number of sides. So from what we have here now, the number of sides is 20. Okay, n is 20. Okay, so it means that sum of exterior angle will just be 360 degrees divided by 12. That will be 30 degrees easily. 30 degrees. So sum of the value of an exterior angle of a polygon with 20 sides is simply 30 degrees. So we move on to the next thing. So of course, we use the idea that interior angle plus exterior angle is 180 degrees. That is how we are able to subtract each one from 120 degrees, 180 degrees to get those exterior angles. So we have a quick table to review the things we've been learning so far. So quick table of common regular polygons. So for an equilateral triangle, which is a regular triangle, the number of sides is 3. Each interior angle is 3 minus 2 times 180 degrees over 3. So that'll be 60 degrees, right? That's 3 minus 2, 1. 1 times 180, 180 divided by 360. So each exterior angle is simply 360 over 3. That's 120 degrees. For a square, the number of sides is 4. 4 minus 2 times 180, that's 360 over 4. That's 90 degrees. So each exterior. So in the case of a square now, each exterior angle is equal to each interior angle. I think the same. Yeah. So we have that. So 90 degrees. 360 over 4 is also 90 degrees. Then for a regular pentagon, 5 sides. So each interior angle is 5 minus 2 times 180. That's 3 times 180, which is 540 divided by 5. That's 180 degrees. Each exterior angle is 72 degrees. Wow, I'm seeing a pattern that is really interesting here. Okay, well, I mean, it is expected, right? So regular hexagon has 6 sides. Each interior angle is 6 minus 2 times 180 divided by 6. This is 720 over 6, which is 120 degrees. That's 4 times 180, 720 divided by 6, 120 degrees. Each exterior angle is 360 over 6, which is 60 degrees. For a regular octagon, that's 8-sided. N is 8. So each interior angle is 8 minus 2, 6 times 8 minus 2. That's 6. 6 times 180. That's like 540 times 2. That's 540 times. That's 1080 divided by 8, which is 135 degrees each. And exterior angle will now be 360 over 8, which is 45. So you see that sum of interior angle plus exterior angle always adds to 180. 60 plus 120 is 180. 90 plus 90, 180. 108 plus 72, 180. 120 degrees plus 60 degrees, 180 degrees. 135 plus 25, 180. So that's established. So let's take example 2 now to drive home the point. Okay. So for example 2, we have this. Interior and exterior angles of a regular octagon. So an octagon is an eight-sided polygon, just like we saw up there now. Okay, so we have find each interior angle, each exterior angle for a regular octagon. N is 8. So each interior angle is simply n minus 2 times 180 degrees over n. So that's 8 minus 2 times 180 over 8. That's 6 times 180 degrees over 8. So that's 1080 divided by 8. That's 135 degrees. That's each interior angle. For each exterior angle, since the number of sides is 8, each exterior angle will be 360 degrees over n, which is 360 degrees over 8, which is 45 degrees. So if you check, so if you are correct, the addition of interior plus exterior angle must give you 180 degrees. And that's true for this. Now, before I go further, I want to quickly talk about the first few polygons, the ones that can be named, okay? I think we kind of saw it before. So first of all, we want to look at the number of the value of n against the n versus the polygon that gives, okay? We want to consider that as much as we can. Let's go as much as we can go. So first of all, like we know already, when n is 3, we have a triangle. Okay? Then when n is 4, we have a quadrilateral. Okay? That's a quadrilateral. I'm not even talking about the regular one now. I'm just talking about general stuff. Quadrilateral. But if you're talking about regular polygon, so okay, well, I think I can still go ahead and put it. Or better still, I can say triangle. For regular, that's equilateral. Okay, equilateral. So what I'm doing here with the one in bracket is when it's a regular polygon, what is it called? So the first few ones have special names, but going forward, they don't really have special names afterwards. So for a quadrilateral, the regular one is a square. Okay. So if the number of sides is 5, you have a pentagon. Okay. You have a pentagon. Then if it's 6, you have a hexagon. Hexagon. Okay, I just want to put out the special names. So then if the number of sides is 7, you have a heptagon. Heptagon. Then if it's eight-sided, you have an octagon. Think about octopus, right? Remember octopus? So you have octagon in this case. Octagon. Octagon. So if it is nine-sided, you have a nonagon. Nonagon. Remember, non-Nigerian, a 90-year-old person, a 90-something-year-old person, right? Then 10 sides, you have a decagon. Okay, we can continue, right? We can continue. I'll go as far as 12 and stop there because the names are still possible. So 11, you have an on decagon, and then n is 12, you have duo decagon. Okay, so you can keep going like that. So those are the first that should be first 10 polygons. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, those are the first 10 polygons. We can keep going. So you can even have like 100-sided polygon. But I don't know what the name is called in that case. But for triangle and rectangle, they have, so when it's regular, you have equilateral and square. But for other ones, you just say regular polygon. The name just keeps on. Regular polygon for when all the sides and angles are equal. So we have regular polygon, pentagon, regular hexagon, regular heptagon, regular octagon, regular nonagon, regular decagon, regular undecagon, regular duodecagon, and so on and so forth. Okay, so we go on again to the next thing. for example 3, find the number of sides from an exterior angle. So a regular polygon has an exterior angle of 30 degrees, right? One exterior angle, but it is regular, right? So the number of sides, we want to find the number of sides and each interior angle. So if you use an exterior angle, one exterior angle is simply 360 degrees over n. That is 360 degrees over n is equal to 30. That means that the number of sides is 360 degrees over 30. That's 12. So that's a 12-sided polygon using this. So one interior angle would just simply be, when you add the exterior plus interior, you get 180. So that means an interior angle will simply be 180 degrees minus the exterior angles of 30 degrees. That's 150 degrees. So this is a regular 12 agon. That's a duodecagon for sure. All right. This is 12 gon. So it's a regular duodecagon, and each interior angle is 150 degrees, as we have seen here. Okay. So next thing, let's talk about area of regular polygons using triangles and apothem. Okay. Now, first of all, we want to split into congruent isosceles triangles. So consider a regular polygon with n sides and side length s. So if you join each vertex to the center, you get n-congruent isosceles triangles. Each has a central angle. So the central angle is 360 degrees divided by n. So see this now. I mean, the basis of this whole thing is okay, imagine if you have an isosceles triangle, okay? So these two sides are equal and this one is different. Then these two angles are equal, but this one is okay. These two sides are equal and this one is different. Then these two angles are equal and this one is different. That's an isosceles triangle, right? Um, in this case now, okay, let's see what the argument is about. So we have the idea of apothem coming up. So consider a regular polygon with n side, then the side length s. Okay. So if you join each vertex to the center, you get n congruent isosceles triangles. So each has a central angle. So the central angle is usually 360 divided by n. Okay. So, well, I mean, I can say that maybe the central angle is 360 degrees divided by n. So that is 360 degrees divided by 3. Okay, maybe that doesn't work in this case. And that'll be like 120 degrees. Okay, so I mean, for instance, if we say that so it all depends on what we are talking about, right? But maybe that doesn't apply in this case. Okay, let's say we have let's use okay, first of all, are we even referring to a regular thing? Yeah, regular. Okay, so it means we are talking about a square, for instance. So this 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, like this. So aha. So we have the center here. So if you draw this and this, and you have this and this, so we end up having 1, 2, 3, 4. We end up having 1, 2, 3, 4, 1, 2, 3, 4 isosceles triangles because this side is equal to this side is equal to this side. So we have 4 isosceles triangles here. I think that's the idea here. Okay, for the other one, I think I should still have got the same thing, right? So if you have an equilateral triangle, so you have an equilateral triangle, all the sides are equal. So if you have the center this way and you join this and this and this, so we have 3 isosceles triangles. So that's 1, 2, 3. Here it's 4. So the angle at the center here, of course, will have to be 360 degrees divided by 3 here. That's 120 degrees. So it means that each of this is 120 degrees. And that's correct because if you add 120, this is 120, 120, 120. Angle at a point is always 360 degrees. So that's cool. Now for this other one now, you have this one. The angle here now will be 300. This is what that thing is called the central angle or something. So it's called the central angle, yeah. So this is the central angle here. Yeah. So central angle. Okay. So for this, the central angle is simply 360 degrees divided by 4, which is equal to 90 degrees. Okay. So that means this is a right angle, this is a right angle, this is a right angle, and this is a right angle. Okay. So with that in place now, we can then go ahead and have other things. So A is called the apothem. The apothem is the distance from center to a side measured perpendicularly. So it means that for apothem now, we have this. So this is our apothem. It is called A, right? And it is perpendicular to the line it's touching. So that is our A. That is the apothem. Okay? Apothem, yeah. So we have apothem like that. So this is A here. So in this case too, you can draw it this way, and it is perpendicular. So that is A. You can have it this way. That is A also. Anyhow you draw it, you can draw it to any direction. But as usual, because this is equilateral, now by the time you draw to the center, you have the number of triangles you have is actually, like we said, it's equal to the number because it's a triangle, we have three of this. Because this is a rectangle, here we have so this is we have isosceles three isosceles triangles, and here we have four isosceles triangles. Okay, four isosceles triangles like that. All right, so with that in place now, we have the next idea that okay, A is the apothem, that's distance from center to a side, measured perpendicularly. P is perimeter of the polygon. And the perimeter of the polygon is once you know one side, just multiply it by the number of sides. So since P is n times S, we can work with P directly, right? We can work with the perimeter directly. And what do we have? We can derive the area formula. So each isosceles triangle has base S, okay? So we can say that this is a base now. So this is base. Each isosceles triangle has base S, This is a base S now. Base S, all the way around it. Base S, okay? Now, based on all of this, we can then have base S, height A, that's the apothem. Area of one triangle will now be a triangle that's half times base times height. That's half times S times the apothem. So half times the base times the apothem. So that's half SA or half AS if you like. Then there are n such triangles. So because there are n such triangles, the area of the polygon will be the summation of all the of the area of all the triangles. So that's n times half times SA. We already have half times SA here. That means that we have half NS times A. And NS is the perimeter of the polygon, interestingly. So that's number of sides times the side length. So the area of the polygon is simply half of the perimeter, half times the perimeter of the polygon, times the apothem. Okay? Half times perimeter multiplied by the apothem easily. Okay? So in that case, now we consider the area formula for a regular polygon for any regular polygon. So if it wasn't regular, we won't be able to say the NS like this. So we have to get yeah, if it wasn't regular, we won't be able to say this. That's all I'm saying. So for any regular polygon, we now have the area is half times perimeter times apothem. That's half times P times A, where P is the perimeter and A is the apothem. Okay? So here now, using apothem and perimeter, a regular hexagon has side length S, which is 10 cm, apothem 8.7 cm. Find its area. Okay? First of all, to find the area, you need the perimeter, you need the apothem. So to find the perimeter, first of all, you just repeat its number of sides times side. For a hexagon, the number of sides is 6. The side length is 10. That's 60 cm for the perimeter. So it means that the area formula will just be half times perimeter times apothem. So that is half times 60 times 8.7. If you do that, you get 261 centimeters squared. So the area is 261 centimeters squared. Okay. Imagine okay, before we go further, let me quickly demonstrate what that is about here. So we are saying that this is now a hexagon, right? So we have a hexagon. That's a six-sided thing. So we have this, 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 and this, okay? It's a regular one. It may not look like that the way I've drawn it, but it's regular, like we said. And what else do we have as in that case? So perimeter is 72 cm. Oh, okay, this example too. So the side length is 10 cm. The apothem is 8.7. Okay. Side length. So it means this is 10 cm. That means each distance around it is 10 cm. So this is 10 cm, 10 cm all the way around. But then for this center, you can have this center now. And then you can have from each vertex, you have this. Okay. You have this, you have this, you have this, and you have this. If you count everything, you have 1, 2, 3, 4, 5, 6 as expected. And then the apothem now is this guy. So the apothem is the height you draw from here. And we said that that apothem is 8.7, 8.7 centimeters. I believe that's what that is over there. So the apothem is 8.7. So you now want to find the area of the, so we now say area of regular hexagon, six-sided, okay, is equal to half times perimeter. Okay, let me take that down. So that is equal to half times perimeter times apothem. Okay? Apothem is that height. So, and the height you can draw it anyhow. It can also come like this. It's perpendicular and it's 8.7 cm. So anyhow you want to have it, it's still the same. So that means you have half times. The perimeter is 10 cm in 6 places. That is number of sides times the side length times the apothem A. So that means you have half times 6 times 10 times 8.7. And of course, it's area. So that's going to be centimeters squared for sure. So that is half times 60 times 8.7 centimeters squared. I think that ended up being like 261 centimeters squared for the area of this hexagon now, like this. So, I mean, that concept is important. So the center, draw the number of isosceles triangles be equal to the number of sides the polygon has. So example 2, from perimeter and apothem. So a regular polygon has perimeter 72 cm, apothem 10 cm. Find its area. That's easy. So you don't have to even find the perimeter because it's been given. So the area is half times perimeter times apothem. So that's half times 72 times 10. That is 36 times 10, which is 360 centimeters squared. The area is 360 centimeters squared. Now, you have equilateral triangle via apothem method. So an equilateral triangle has side length S, 8 cm, and its apothem A is 4 root 3 cm. Find its area using the regular polygon formula. That's easy. Okay, I mean, what we are simply saying here is that this is now an equilateral triangle with side 8 and apothem 4 root 3. Okay, so that's thinkable, right? Because we've tried it, we've done it before already. So you have an equilateral triangle, right? All this. Okay, so you have a center. I have to be careful. I need to, of course, I'm not trying to be, I want to be just want to be as accurate as possible, though it's hard to get the actual thing. So you have the center now. Okay, so if you draw this, and draw this, you have this three isosceles triangle, this 1, 2, 3. And then, so we are told that each side is 8 centimeter. And then for the apothem is like the apothem, you can draw it this way, and that is 4 root 3 centimeters. Okay. So area of triangle, it's regular triangle now. So area of equilateral triangle, area of equilateral, because that's the equivalence of a regular polygon. Area of equilateral triangle is equal to half times perimeter times the apothem. Okay, so that's half times perimeter, that's number of sides times the side length times the apothem. So that is half times number of sides is 3, the side length is 8, and the apothem is 4 root 3. Okay, so we have 24 times 4, that's 96 root 3. And we can even break that down, 96 root 3 centimeters squared. Okay, what did I do there? Maybe not quite. This is 2 here is 1, 2 here is 4. 4 times 4 is 16. 16 times 3, that's 48 root 3 rather. 48 root 3 centimeters squared. That is the area of that equilateral triangle, 48 root 3. centimeters squared like that. Okay. And if you root 3 is 1.732, so you can multiply out and get it. So we can approximate circles via regular polygons. So approximating circles via regular polygons. So the idea you have more sides is means closer. The more size a polygon has, the closer it is to a circle. Okay, that's the idea here. So because as more sides are added, it's like shaping up more like a circle. So consider a circle with a regular polygon inscribed inside it. So you have a regular polygon with a circle inscribed inside it, all vertices on the circle. So as the number of sides n increases, the polygon looks more and more like the circle. So to compare the perimeter of polygon versus circumference of a circle, you can compare. So area of polygon versus area of circle, this are another, you can also consider compare the area of a polygon with the area of a circle. So for a circle of radius r, circle circumference is 2 pi r, whereas the circle area is pi r squared. As n gets larger, that is the number of sides of a polygon gets larger, the polygon perimeter gets closer and closer to 2 pi r, while the polygon area gets closer and closer to pi r squared. So this helps us understand pi as the ratio between a circle circumference and its diameter. So that's something to think about. Okay. So let's see this regular hexagon in a circle. So take a circle of radius r with a regular hexagon inscribed inside it. Fact, each central angle of the hexagon is 360 degrees over 6. We already know that. That is if you draw equilateral triangles like that, like we said before. So each triangle from the center is equilateral. So you have sides r, r, r. So side length of the hexagon is equal to r. So perimeter of the hexagon will just be 6 times x or 6 times r. So circle circumference is 2 pi r, which is approximately 6.283 r. And the ratio is like perimeter of the hexagon over circumference of the circle. That's 6r over 2 pi r. So if you simplify, that's 3 over pi. That's approximately 0.955. So the hexagon's perimeter is already about 95.5% of the circle's circumference. So you can use, so if you now increase it to, say now, instead of having a hexagon, and maybe you now want to have like let's say a 20-sided thing, right? 360 over 20, that's 36 over 2, that's 18 degrees. So if you have 18 degrees here, so instead of this 6, so uh you now have okay, this is 20 sides, right? So you have 20 s over 2 pi r. The value is, so in that case now, 20r over 2 pi r cancels out. So you have 20 over 2 pi. That's 10 over 2 pi r. So, I mean, you have something even larger. I'm not sure I'm getting that right, but I mean, that's the idea. You can actually approximate a circle using a polygon. So let's talk about numerical comparison. So take a circle with radius r equals 10 centimeters. So circle circumference is c equals 2 pi r, which is approximately 2 times 3.14 times 10, which is 62.8 centimeters. So inscribed regular hexagon, the side length is s equals r, which is 10 cm, and the perimeter of the hexagon, that's 6 times 10, equals 10 cm. So hexagon perimeter is approximately 60 centimeters, and circle circumference is 62.8 cm. So if you use polygons with 12, 24, 48, 96 sides, their perimeters get even closer to 62.8 centimeters. Historically, this method using many-sided polygons was used to approximate pi. Okay, so that's one way pi came into play. Now, because this video is almost 1 hour, I think instead of going on with tessellations, I'm going to make that into another video. All right, so watch out for the next video where I'll be talking about tessellations. All right, thank you so much for listening. Let me know how helpful this is for you. Before I go into that, of course, I was supposed to talk about tessellations here, but I won't talk about it because the video is already long. So what I'm going to do is, so I'm just going to show you some questions related to hexagon here. So you want to practice this. A regular hexagon has side length 9 cm. Find its perimeter, find its interior and exterior angles. A regular polygon has interior angle 114 degrees. Find its exterior angle. How many sides does it have? I can already get this like a decagon because we've done it before. A regular octagon has side length 5 cm and hypotenuse 6 cm. Find its perimeter, find its area using this. Then you have other questions like that. Okay, I think every other thing is about tessellation except this last one too. A regular polygon has an exterior angle of 24 degrees. Find the number of sides of the polygon. Find each interior angle. Determine whether this polygon could be used in regular tessellation of the plane and all of that. Okay, so we have all this. So I'll do another video focused on tiling, tessellation is like the process by which you lay tiles and things like that. So watch out for that in the next video. Thank you so much for listening to this very interesting video about regular polygons. I'll continue with the tessellations in the next video, like I said already. So try your hands on the practice questions. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. Okay? If you have subscribed already, I thank you very much. If you haven't, why not go ahead right away and hit on the subscribe button. And of course, don't forget to uh, click the notification bell so you can always get alerted each time a new video is released. Having done that, you can become a member of the channel. So that comes some special privileges. Ultimately, don't forget to comment, like, and share so that more people can have access to this great content I have going on here. Till I come your way again, keep doing maths right. Watch out for tessellations in the next video. Bye.